Okay, so today we're going to try to apply everything that we've learned about waves, which of course you remember, to the world of sound. So we're going to be asking the questions, what is sound? What are the properties of sound? How can we study and understand sound? How does sound reach the human ear? And then how does the human ear and the human brain make sense of it? You guys are all listening to my voice. You're hearing the sounds coming out of your computer speaker. How, by the way, is it possible that my voice, the sound waves that I am emanating from my vocal cords right now, are going somehow magically into my computer, being recorded in a digital format, being transmitted through Wi-Fi, whatever the heck that is, to your computer, and then out through your speakers? How is that possible? That is the magic of the modern world, is it not? Of modern technology. And that's what we're going to be studying actually next time, not this week, but next time, communication technology. But in order to understand that, we have to understand the basic properties of sound. What is sound? How can we understand it? How does it reach the human brain? So what I have here is a wave, and hopefully you guys remember what type of wave this is. It is a longitudinal wave. How do I know that? Because I see that the particles are vibrating back and forth in the same direction, the same dimension of motion as the wave itself is traveling, left to right. Focus on one of the red particles here, you'll see that it's oscillating, vibrating left to right, and the entire wave system itself is moving from the left to the right. So this is a longitudinal wave. What is a wave, by the way? I think we defined it as energy passing through a substance, causing the particles of that substance to vibrate or oscillate. This is just a review, because if we're going to understand sound, we've got to understand waves. Sound is a form of a wave. So this was a longitudinal wave. This is a transverse wave, because each individual particle is moving perpendicular to the motion of the wave. Each particle is moving up and down, yet the wave energy is passing from left to right. So what is sound? Sound is a type of wave, and remember, waves are just energy passing through substances, so we could almost call sound a type of energy. It's a longitudinal, sometimes called a vibrational wave, passing through the particles of a medium. Usually the air is the medium that we're talking about. So a sound wave is really just vibrating air particles. Sound is wiggly air, right? So the vocal cords in my voice right now are vibrating with certain frequencies and certain amplitudes, and those vibrating vocal cords are vibrating the air particles around me, and that is the sound wave leaving my mouth right now. So sound waves are always themselves caused by the vibration or excitation of a nearby object, whose vibrations cause the air particles themselves to vibrate. So once again, my vocal cords are vibrating, that causes the air particles to vibrate. Those vibrating air particles, the vibrations get passed on and on and on as the wave energy moves throughout the medium, through the air. That's a sound wave. Notice that I'm saying it's longitudinal. It's a longitudinal wave, just like this. So if we now understand all these dots as representing particles of the air, the gas particles in the air, then this would be exactly a sound wave. So imagine that I'm over here on the left side, or it could be a speaker or a guitar string or your hands clapping or a drum or a cymbal, anything that can vibrate my vocal cords. And those vibrations cause the air to vibrate just due to collisions of particles, right? The air particles get excited. There's some energy put into the system. The air particles now start to vibrate as a wave, so they start to oscillate back and forth, left and right. And they pass on that excitation. They pass on those vibrations. That energy moves through the system. You can see the wave energy moving from left to right, causing the particles of the air to oscillate left and right. This is a longitudinal wave. Sound is just longitudinal waves of air particles, usually. Remember that we have special terms for longitudinal waves. We don't really talk about peaks and troughs. Instead, we have these two words that are moving down here, compressions and rarefactions. Those words are going to be important in this week's content. A compression is the part of a wave where the particles are really close together. So here you can see is a compression. A rarefaction is the opposite. That's where the particles are very, very far spread apart. So we can also say that sound waves then are longitudinal waves, or sometimes we call them compressional waves, or waves of compressions and rarefactions. The air particles are going to get shoved close together, spread apart, shoved close together, spread apart, etc., etc. This is a sound wave. Once again, it's always going to be due to a vibrating object. That vibrating object excites or sets into motion, sets into vibration the air molecules, the air particles, and those will vibrate back and forth, carrying that sound to your ear. So when my brain tells my vocal cords to vibrate with a certain low pattern, that's going to cause the air to vibrate in that exact same pattern, and it's going to get picked up by your ear. If, however, I tell my vocal cords to vibrate in a high pattern, then that pattern is going to get passed on through the air. Sorry, I couldn't keep that up for long. That pattern is going to get passed through the air particles, and enter your ear as well. So notice that we can really think about this as information being transferred, right? The vibrating object is putting some information out there in the world, low vibrations or high vibrations. In the case of my voice right now, different vowel sounds, consonant sounds, which due to human language we know is words and sentences and thoughts and ideas and things like that. And that information goes out and is translated into a new form, the vibration of air particles, and that gets received by you, the listening organism, and your brain will ultimately, hopefully, be able to perceive that. So I'm just trying to get you thinking about all of this in terms of information transfer, because that's what we're going to be looking at next week. Really, all this is about energy being transferred from one form to another. Kinetic energy of particles vibrating in this object, that energy gets transferred to vibrational energy, wave energy in the air, which is going to get transferred in your ear as another type of energy. It turns out it's going to be electrical energy because of the nerves that you have. And that's going to end up in your brain. So really, all we're talking about is energy. Energy getting transferred as a longitudinal wave through the air. That's a sound wave. You may have noticed this little note that I put down here. If a tree falls in the forest and there's no organism around to hear it, does that tree make a sound? You guys have heard this silly little philosophical riddle before, I'm sure. Well, in my mind, this actually has a definite answer. What do you think the answer is? To me, the answer is no. Because by definition, a sound requires that it be capable of being received as sensible information by some organism. If there's no organism around capable of receiving that information, capable of receiving the sound wave on the other end over here, if there's no ear around, then by definition we don't really have a sound. We do have a wave, we do have vibrating particles. This would still happen if the tree fell in the forest, big time. There'd be a big sound wave passing through the air. But would it be sound? No, I don't think so. I think sound requires both a sound wave, vibrating air particles, and something there to perceive it, something there to pick it up. We'll talk about the perception, the receiving of sound, how your ear does that, how your brain does that. We'll talk about that more next week. We'll talk about that more this week in the next video. I want you to know that sound can also be defined as what we call a pressure wave, as a transverse pressure wave. So remember, a transverse wave is one where one that goes up and down. And again, you know, compressions, rarefaction. So here's what I'm getting at. Let's look at this picture up here. If here's my sound wave, kind of frozen in one moment in time, you know that C would represent compressions. That's where the air particles are colliding with each other. They're compressed. They're close together. R represents what? Yeah, rarefaction. That means that the particles are spread apart from each other. So we've already said that sound is a longitudinal wave causing compressions and rarefactions, moving through the air. Well, think about it. If we had some special device that could measure the air pressure, the pressure of these particles. Now, do you remember what pressure is, where that comes from? We talked about it a little bit a long time ago when we were discussing the phases of matter. Yeah, pressure comes from the collisions of little particles. So where in my diagram here, where in my sound wave am I going to have highest pressure? Wherever I have a compression, right? The particles are close together, they're colliding. So every compression would correspond to high pressure. And every rarefaction, right in the middle of the rarefaction, the particles are so spread out, I don't have a lot of collisions between particles. I have very low pressure. So we can think about sound as a pressure wave, as this kind of mathematically mapping the compressions and rarefactions, high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. That's going to change as time goes on. That's what this diagram is showing as well. Really, sound is just changing pressure. Like I said, wiggly air, right? Wherever the particles are in a compressional pattern, they're colliding, they're close together, that's high pressure. Wherever they're in a rarefaction pattern, they're spread out, that's low pressure.